afternoon, everyone. So today I have the pleasure of introducing Professor Harish Vedantham from ASTRON. Harish started his career working on H21 at the University of Groningen, but now I think he has made a very different size scale change from looking at large scale cosmology to now exoplanets and brown dwarfs. So today he'll be talking about flashes from plasma storms around exoplanets, and let's welcome him. And yeah.
Thanks a lot. Yeah, thanks, Mayank. Thanks for hosting me here. I've been having a great time interacting with many of you. So I'll tell you a little bit about the work I've been doing in the last roughly 5 years. As Mayank said, I was working on something completely different before that. And this mainly has to do with radio emissions from stars, brown dwarfs, and exoplanets. And of course, radio emissions from stars themselves are intrinsically interesting. But a lot of the motivation for the work just we are doing particularly is to understand what we can learn about the impact the star has on the exoplanet. And so hence the title. I'll still be speaking about radio emissions from the stars themselves. The other comment I want to make before we begin is I very quickly realized when I started working in this field that most radio astronomers don't do stars or exoplanets, and most stellar and exoplanets astronomers don't do radio astronomy. And so I quickly realized that it goes a long way for me to have some more introductory and pedagogical material. So I'll spend more time on that, but there are results coming in the end, so hold tight. But it also means that I need to lose something to gain something, and the thing I'm going to lose will be a lot of the history of the field, of the work which is being done. And of course, I also won't have time to highlight some of the works being done by other groups around the world. So I'll focus mainly on the work we are doing in my group. So apologies to my current collaborators and the people who have come before me. I am standing on the shoulder of giants, but I won't be able to make full justice to that in this talk. Okay. I also want to say that a lot of the work I'll be showing has been done by students and postdocs, so that's my group. Top row are the PhD students, and they're always this happy when they're working with me. And there are 2 postdocs right now in the group, so a lot of the work is being done by these people. Okay, so I want to start with a thought experiment. So let's do a thought experiment, but we're going to do it with real data. Okay, so maybe this is the first thought experiment with real data you have done. So assume that you are an alien civilization, you're looking at the solar system, you don't have the angular resolution, the entire solar system is in 1 pixel. So all you can do is measure the brightness, polarization as a function, the brightness as a function of polarization, frequency, and time. And you need to figure out what's happening in the system by what you see in that 1 pixel. So we have real data on solar system objects, and that is what it will look like. So this, I'm forgetting polarization for the moment. So this is a spectrum, it's flux density in Jansky's y-axis, wavelength in microns on the x-axis. And what you see here is largely what you would expect from Planck's law. That's what you're seeing there at short wavelengths at least. You see some enhancement at the ultraviolet wavelengths, at the shortest wavelengths. That's because of a lot of activity which happens on the sun. And then you also see that there are some lines here. That's because of radiative transfer through the atmospheric layers in the sun. And then this is the long Rayleigh-Jeans tail, which you would expect. But black is measured. And so when you come to very long wavelengths, the solar system doesn't look like what you would naively expect it to look like, which is you basically see the sun and nothing else. And so I'm just going to ask anyone in the audience to get what is happening here. Any guesses from the audience? Yes? Sorry? Interestingly, this component is related to the chromosphere, but it's not coming from the chromosphere itself. Actually, the chromosphere is optically thick at this wavelengths already. Yeah.
Stellar magnetospheric sphere?
Yes, so this actually is coming from, this is also coming from a magnetosphere. It's just that it's not the sun's magnetosphere. So that's the interesting part. So that component there is Jupiter. It's actually brighter than the sun at these frequencies. And this bump you see here is the quiescent sun. And the reason you have a bump here is this is basically incoherent synchrotron emission. So these are relativistic or mildly relativistic charges stuck in the magnetic field loops of the sun, emitting incoherent gyrosynchrotron. It's called gyrosynchrotron, but the basic idea is the same. It's like synchrotron with mildly relativistic charges. And this is actually cyclotron emission. So this is a coherent emission mechanism, and this is basically Jupiter. And of course, once you have measured this component of the emission, and I'll show you some examples of this, you can figure out a few things which are very hard to figure out by other means. One is you can figure out what is the magnetic field strength of Jupiter, and you can figure that out by looking at where this emission cuts off. Okay, that has to do with the cyclotron frequency at the surface of the planet. You can figure out what the rotation rate is, because this emission varies periodically because it is beamed, so it's like a lighthouse. You can also figure out the presence of moons, because a part of this emission is induced by the moon Io and the other moons, and you actually see modulation at the orbital period of the moons and not just the rotation period of Jupiter. And of course, you can do a lot of, if you like physics, you can do a lot of physics of acceleration of charges in a magnetosphere. So that's pretty interesting. It's, yeah.
Perhaps we explain it later, but is it sensitive to solar activity?
And so even if the sun weren't present, Jupiter would still be a bright radio source, because the source of plasma is volcanism by Io. The sun does have an effect on the size of the magnetosphere, so it does have a modulation. So if there's a coronal if the solar wind pressure increases, it compresses the Jupiter's magnetosphere, and that has other effects. But a lot of the emission here is rotationally powered in Jupiter. Yeah. Okay, and you would also observe that every now and then something crazy happens, and this is actually the sun. So there are times when the sun will just outshine everything, and this is when there is an energetic event happening on the sun. And a lot of these are eruptive events which lead to coronal mass ejections and things like that. And of course, that has an effect on the atmospheres of the planets. And so you actually get another nice window into what's happening to the space weather around the exoplanets by looking at the star itself, about what it's doing. So this is the disturbed sun. It tells you about the presence of coronal mass ejections. Some of these bursts are created by relativistic beams which are emitted by the sun, which actually can have an effect on the chemistry of atmospheric chemistry of planets. And of course, if you had a good student and you observed this solar system in a pixel, you could in principle figure out the energetics and rates of these things and try to figure out what's happening to the planets in this system. Okay, so if I have to kind of summarize everything I've said, what radio is really good at probing is non-equilibrium plasma. So it's not the thermal emission from the corona or the chromosphere which you're looking at, even though that can be detected at high radio frequencies. At the frequencies I'm talking of, centimeter and meter wavelengths, you're really probing non-equilibrium plasma and the presence of magnetic fields. These are all the emission mechanisms which I'll speak about in a minute. So in the slightly higher frequency end, you're looking at synchrotron, like I said, which I won't be focusing on for the rest of the talk. And so most of the talk and my work is actually at these low frequencies where you really have signatures of these space weather events. And that's created by a mechanism called plasma emission, which I'll explain. And of course, some emission called cyclotron emission from the magnetospheres of the planets in the solar system. And of course, I also spoke about these interactions which also induce this kind of emission, just like Io induces emission on Jupiter. So that's what we are really looking for. And so the main idea behind this talk and a lot of the work in my group is we have done all of this in the solar system. Let's try to do it in around other stars and around exoplanets. And of course, there's a huge jump in sensitivity, because you know that 1 AU is about 10 to the 13 centimeters, even 1 parsec is 10 to the 18. So the square of that is what kills us. But there is some new instrumentation which is making some of this possible, which is what I'll talk about. Okay, so that's what I want to know. So in the solar system, we have this beautiful picture. We can actually make artistic renderings. We don't know much about what's happening in an extrasolar system. And so while in the solar system, we have the detail of an artist who made this picture. This is my hand drawing, and this is the level of detail we know. But that's the basic idea there. I'm looking at interactions in non-equilibrium plasma in a star-planet system. Okay, so I'll give you some examples of the emissions in the solar system. So it's a good benchmark. So you can actually interpret the rest of the data on extrasolar systems I show you. So this is basically all the radio emission from a sun in one graph. We don't have to go through all of that for this work which we are doing. What is important for us is some peculiar structures in the time frequency plane. And those are these green things here called type 2 bursts, and these red the violet things here called type 3 bursts. And so type 2 burst is actually created by a coronal mass ejections. It actually requires the presence of a superalphanic shock. So it requires the expulsion of a large mass of plasma. And what's happening here is that the emission is by the plasma mechanism, which I'll explain soon, where the emission frequency only depends on plasma density. So as the shock is moving out, it's going into regions of lower plasma density, so you get emission at lower frequencies. And that's why you get this sweep. So the moment you see that sweep, you know that plasma is getting unbound from the star and going into the interplanetary medium. So that's why that's a fantastic probe of the presence of coronal mass ejection. The same idea happens in a type 3 burst, but that is created by a relativistic beam of particles. And because the beam is relativistic, of course, it's moving faster. And because of that, the sweep happens much faster. So a type 3 burst happens on a second time scale, type 2 burst happens on minutes time scale. It's the same idea, it's just different velocities. So we want to find these kind of things on stars other than the sun, which hasn't been done before, right? And so that's one motivation. So here's some details for students who would be interested in the emission mechanism itself. So the mechanism is called plasma emission. It has a few steps. It's actually, it's a nonlinear emission mechanism. You need to have some beam of hot plasma, like you need to have some fast electrons, so faster than thermal. And because they are moving much faster than the phase velocity of Langmuir waves in the medium, you get Cherenkov emission of Langmuir waves. And that Cherenkov emission of Langmuir waves develops a Langmuir wave turbulence. So you can think of this as turbulence in similar, it's like a density turbulence, but in a plasma. So the restoring force of the Coulomb attraction is also important in this turbulence. And that has to be converted to an electromagnetic wave. And this turbulence occurs very close to the plasma resonance, so the plasma frequency, which is why when you conserve, in this conversion, when you conserve energy and momentum, you get an electromagnetic wave out very close to the plasma frequency. So that's the equation for the plasma frequency. So in Gaussian units, so if the density is about 10 to the 9, typical density at the surface, at the base of the corona in the sun, you get emission at about 0.3 gigahertz. And then the emission frequency goes down as the burst moves out. Yeah, and of course it can produce very high brightness temperatures because it's a coherent emission mechanism. So the hope is that we can have these bright events which we can detect from stars other than the sun if we stare long enough at these stars. That's the point. Okay, so let's get to Jupiter's magnetosphere. I told you about the sun, so you can call that sun-like emission. This is what happens when the plasma frequency is more than the cyclotron frequency. So it's, if you think in terms of the plasma beta parameter, it's one end of that range where the plasma dominates the magnetic field. And here we have the magnetic field dominating the dynamics instead of the plasma itself, the inertia of the plasma itself. So that's what we have here. So this is an example of Jupiter's radio emission, and this is just the occurrence of bursts as a function of Jupiter's rotational phase and Io's orbital phase. And you can see that the bursts are grouped in this plane. And the reason for this is again this beaming effect, this lighthouse-like effect which I told you about. Every time Jupiter rotates, you get a rotationally modulated pulse, just like in a pulsar would do, but the beaming pattern is more complicated than in a pulsar. And of course, some emission components are controlled by Io, and I'll tell you why that really happens. It's a very interesting reason. Of course, if you zoom in here, you get, it has, so when you pick up the cup, this goes off. I'm not saying they're causally connected. Correlation is not causation. Okay, anyway, yeah. Okay, so what you're seeing here are a lot of microphysics. So this is cyclotron, but it is maser emission. It's coherent cyclotron emission. So you're seeing individual charge bunches moving in the magnetic field. And as they move in the magnetic field, they drift in frequency because the cyclotron frequency is changing as they're drifting. So you really get a good idea of not just the field strength, but if you like MHD and if you like plasma physics, you actually get a lot of idea of the microphysics on tens of kilometer scales on these objects by looking at these drifts. So also something fun. So anyway, the emission happens at the local cyclotron frequency that only depends on the magnetic field strength. And so it's one way to measure remotely magnetic fields in astrophysics, the other one being Zeeman splitting. So these are the two ways you can directly measure the magnetic field. One of them is to look for cyclotron emission, and Zeeman splitting is not going to be feasible once the objects become extremely cold, like the coldest brown dwarfs or exoplanets. And so the current thinking is this is the only way we will be able to measure these fields. I'm actually not sure why it's flashing because my laptop's not flashing. So, okay, we'll see how it goes. Okay.
So there's only a delta n of one transition
Sorry?
I mean, cyclotron, you only get a single transition.
Yeah, this is a non-relative. Yeah, in the non-relativistic limit. So this is true only in the non-relativistic limit.
You can't, there's no harmonics on relativistic.
To get harmonic, you need to have the electron be mildly relativistic. A non-relativistic electron, most of the energy will go into just the fundamental.
Because the spin flip of the electron has the same energy, so if you have both the spin flip and the transition, then you get twice. Then you get a harmonic effect of 2.
But you're talking of Zeeman effect.
No.
Not.
Well, Zeeman for a cyclotron happens to be identical to the delta n itself.
No, but here what will matter is the transition between Landau levels.
Yeah, Landau levels between electrons are the same as the Landau levels in hyperfine.
Yes, yeah.
So, but they're split by fine structure.
Oh no, but in radio wavelengths that split is so tiny it's almost irrelevant. The Landau level energy split is too small at these.
It's not just I thought it is just cyclotron.
It is, yes. But at radio, at these, with this magnetic field strength,
Yes.
And the typical energy of electrons, which will be 10 to 100 keV, the split in Landau levels are so tiny in that it's almost like a continuum. You can treat this classically.
Identical.
Yeah, the equation for cyclotron resonance is identical. But when you derive the amount of energy emitted in different harmonics, you can treat this classically. It's valid basically. And there so if you treat it classically, then you actually it's actually the aberration of light which gives you the higher harmonics in cyclotron motion. In the absence of aberration of light, you do not get in the absence of relativistic effects, you cannot get higher harmonics because the motion is happening at one particular frequency. So the acceleration is varying at a cyclotron.
Okay, so in the hydrogen, the n equal to 2 to the p to s transition splits by hyperfine.
Correct, yeah.
And this is also split by hyperfine. But the hyperfine is the exact same spacing as the original Landau. It's the same 2.8 megahertz. So shouldn't it split into 2.8 and 5.6?
But what I'm saying is that the difference between the Landau levels
Exactly 2.8.
is not this.
Isn't it?
This is not the difference between the Landau levels. This is the cyclotron frequency. It's not the split in energy between the Landau levels. That's extremely small compared to this, I think. I haven't done the numbers for such low magnetic field strength, so maybe we should, we can maybe take this up after the talk, yeah. Okay, so what is the engine? So you need to create some engine to power this emission. In the sun, it's flares and all kinds of things. In a magnetosphere of Jupiter, it's really like an electric motor or a dynamo. So you need some kind of relative motion between the magnetic field and the conducting medium, and just to use Faraday's effect. That's basically what is causing this. So what's happening is Jupiter has a strong magnetic field, it's spinning, and if the plasma doesn't co-rotate, there is a differential motion, and by Faraday's law, you know there is an electromotive force on the plasma, which is what finally powers all this emission. So it's really spin powered. So it can happen in two different ways. One is Jupiter can do it by itself. If the plasma is not co-rotating, you create an electromotive force which can drive a current, and in case of Jupiter, it's about 1 billion amperes of current, which flows between the magnetosphere and the circuit closes in the atmosphere of Jupiter. And that's what is powering the radio emission. And of course, if you have Io has a conductive ionosphere. So again, it's like moving a conductor across magnetic lines of force. And you again get an electromotive force from Faraday's law, and that creates a current roughly equivalent in power in case of Io. So we there's been a speculation for a long time that this must be a very common setup. As long as you have a low beta plasma, which is to say cyclotron frequency much larger than plasma frequency, so low plasma density, high magnetic field strength, like a magnetosphere, these kind of things should be common. So it should be common among gas giant planets, brown dwarfs, and it should also be quite common to have this kind of interaction between two bodies generating the radio emission. Okay, some theory behind the cyclotron maser. So the reason you get this kind of masing action is because when electrons are trapped in a magnetic field, in the dipole field, they keep mirroring between the two poles. And the reason why they mirror, it just has to do with basic adiabatic motion of the electrons. So the energy is conserved and the magnetic moment is conserved. And so I won't have time to go into the details, but you can very simply show that by just conserving energy and magnetic moment, in the motion, you create this kind of a loss cone geometry. So this is the momentum distribution of electrons. This is the momentum perpendicular to the magnetic field, parallel to the magnetic field. And you kind of deplete these electrons here, and you deplete them because they actually go and strike the surface, whereas the other electrons are reflected. And this is an unstable distribution, and this instability causes the radio emission. Yeah, but anyway, the theory is for people who would appreciate some details, but it's not important that we know the details of it for the rest of the talk. Okay, so let's go to extrasolar systems finally. I did this long primer on the solar system, so I hope everyone is roughly on board with the phenomenology of the emissions we are kind of expecting. So let's go to extrasolar systems, and so let's just go there by remembering that I showed you right now examples of the sun on one end of this and Jupiter on the other end of this, and nature produces everything in between. Okay, so let's just keep that in mind. Actually, do we know why this is happening? Huh?
You're not trying with the EMR.
Oh, you mean there's a loose contact somewhere? Oh. If there is, it's not on this end. These look pretty solid. Okay, let's see how it goes. Okay, yeah. So let's just keep in mind that we have all kinds of things in between, right? And so we will have this transition at some point between a high beta and a low beta plasma, a place where you have like a sun-like activity with like a dense corona and flares which are producing all of these particles, to a Jupiter-like activity where you have low density magnetosphere, and it's not like flares which are producing all these particles. It's this kind of forces which I spoke about, the induction because of motion of plasma with respect to magnetic field, so magnetospheric acceleration. Okay, so a lot of the work we have been doing is thanks to the low frequency array, which many of you might have heard of. This is a low frequency radio interferometer, so the frequency range is 30 to 200 megahertz, but a lot of the results I'll show would be at the higher end of this frequency, simply because it's technically easier to make images at the higher end of this frequency. At the lower end, I'll show some progress we have made, but it remains quite challenging to make deep images at the lower end. It has a large collecting area, about 0.1 square kilometers. It has a large field of view, and that's important for us because you do not know on a given star when a coronal mass ejection is going to happen. And just like this Jupiter's emission was rotationally modulated, you do not know when the beam is going to cross your line of sight. And so you just have to simply have long observation periods to be able to catch a signal, and it's difficult to take over the telescope over long observational periods because other people want to do other things. But if you have a large field of view, there is always a star of interest in the field of view, and so you don't care who's taking the data because there is always some star which is nearby enough within 16 square degrees which you can focus on. So that's what what makes a lot of this possible without us really taking over the telescope over long periods of time. Okay, so the strategy we have is there's a survey going on with this telescope. The entire data set will be 15 petabytes. We cannot process all of it just with a few graduate students. And so we are part of the survey's collaboration, and a lot of the software was written by them. So I want to acknowledge a lot of the work done in the LOFAR survey collaboration. So what we are looking for is circularly polarized sources, and the reason for that is cyclotron emission is circularly polarized, whereas almost no other radio source with the exception of pulsars is circularly polarized. And so you can get rid of a vast majority of radio sources and really find the sources you're interested in. And once we find a circularly polarized source, we know it has to either be a pulsar, which we can try to check by looking for pulsations in follow-up observations, or it has to be a star producing cyclotron maser emission, or a brown dwarf, or an exoplanet, or the kind of sources we want to look at. Now the second part of the pipeline which we developed is to look for this swept frequency bursts. So this type 2 and type 3 bursts which show coronal mass ejection. So we do that separately from the search of circularly polarized sources, and there because we want to look for the space weather causing events. Okay, so that's what we are doing, and for the rest of the talk I'll just present a sprinkling of different results we have so far from this, and then maybe end with some kind of a prognosis for the future of what we might do. So here's what we see when we look at the Stokes V sky in the survey. So these are all examples of Stokes V sources, so circularly polarized sources. So each frame here, each postage stamp here is a different source, and the inset is Stokes V, and the main image is Stokes I. So you can see that all of these are circularly polarized sources. Many of these are 100% circularly polarized, and if you take all of these sources and you match them with a catalog of known stars, let's say Gaia's catalog, with proper motions applied, they all land up on stars. So we are fully confident that these sources are actually emitted by either the star or something in that stellar system, in that pixel at least, which we cannot resolve. So you put them on an HR diagram of stars, they kind of break into two populations. So on the top here, a lot of these are close binaries. They're RS-CVN systems. And again, I think they are very radio bright because of the differential motion between the plasma and the magnetic field, which is actually driving the emission, just like it happens with Jupiter and Io. But of course, if you have two stars, then the energetics are just way more feasible for you to make a detection. So we detect a lot of those. I won't have time to go into the physics of those systems, even though they're interesting. And then the rest of the stars are M dwarfs. And so we asked the question, why are we seeing only M dwarfs? Where are the K dwarfs? Where are the G dwarfs? So initially we thought, well, maybe because M dwarfs kind of have magnetospheres like Jupiter rather than, like a solar-like atmosphere, and we are seeing cyclotron emission from these M dwarfs. That's what we're looking at. And so we kind of tried to test it just on a population level. So this work done by Timo, a PhD student. And so we simply took this survey of all the detections and we made a cumulative distribution function. So on the x-axis is effective temperature, and this is the CDF of all of our detections. Okay, and then we just compare it with what we know already exists in the sky to within some distance horizon. And so that's the broken line. The broken blue line here is the CDF of all the stars that exist within our distance horizon. And so you can clearly see that, and these shaded regions are basically the CDFs of the detections we have from the LOT survey. That's the LOFAR survey, and then the gray here is a survey which is being done with the VLA at a higher frequency at the gigahertz range. And so you can clearly see that some of these actually deviate. So you can kind of see that there is some evolution with spectral type. And so one thing we postulated was that it's probably the existence of these large scale dipole fields in M dwarfs which is causing, making them to be very bright in the radio. So let's test it on one star. So we picked one star, which is AU microscopy. So it's a young M dwarf. We got 250 hours of data on this one star with the compact array in the southern hemisphere, and Sana, who's my PhD student, actually observed for 250 hours and reduced 250 hours of data. And once you have data like this, you can do a lot of things which you couldn't otherwise. So she just plots this on the rotational phase of the star, and you can see that all the bursts you get are completely confined to two phases in rotation, just like you saw with Jupiter. It is that kind of rotationally modulated beaming which you are seeing. And so we try to, a lot is known about the star. So we know the inclination of the star, we know the magnetic map of the star with Zeeman Doppler imaging. And so we can try to make a model for when the radio emission should cut across your sight line. And so with some very minimal assumptions, we can easily create a model which is shown in the bottom half here, which tells you the visibility of the radio emission. Of course, we cannot exactly predict the magnitude here, the brightness, because it's a coherent emission mechanism. So it can be highly variable in brightness, but the visibility is predicted almost perfectly. So this kind of, I would say, take it as very strong evidence that in M dwarfs already you have kind of a magnetospheric phenomena which you actually see on Jupiter. You have cyclotron emission which is rotationally modulated, and that's quite interesting. That already in M dwarfs you have this kind of magnetosphere. So their corona look very different from the solar corona.
What is the kind of orbital period of this star?
The rotation period is about 4 point something days. Yeah, that's why we need 250 hours. Pulsar astronomers won't understand our pain because they have to observe for like 10 minutes and then they get several rotations of the object, and we have to do days of observations. Yeah.
So does the flux go to zero in between these? Does it go to zero?
Yeah. In some epochs, it's just not detected. I mean, it's a compact array, so it's not the most sensitive telescope on the planet. But yeah,
I should show you some of my GMRT work.
Sure. Yeah, we should see that. Yeah. Okay, this is work done by ASIAA, who's a Chinese scholarship student who's spending half of his PhD with us. And so this is again data on a single star, AD Leo, taken with the FAST telescope. So what you're seeing here is Stokes V emission on different time scales. So notice here the x-axis. As you go from above to below, you're zooming in more and more. And so again, if you remember Jupiter's emission, which I showed you the microstructure where you can follow individual charge bunches as they're moving in the magnetic field and sweeping in frequency. So you see exactly the same kind of phenomena on AD Leo. And so what you're seeing here is extremely fast drifts on millisecond scales. The drift period is 7.5 gigahertz per second of drift. And you can actually, these are individual charge bunches emitting cyclotron maser emission moving in the magnetic field. And as they move, they are moving in frequency because the cyclotron frequency is changing. And so you can reuse that and say the fastest this charge bunch can move is the speed of light. It can't move faster than that. And so how big is the structure, the magnetic structure, which will give you this sweep. And so ASIAA was able to show that this drift requires the structures where the emission is happening to be about 0.1 times the radius of the star or smaller. And so this tells us that M dwarfs are a little bit like the Sun but a little bit like Jupiter. They do show this kind of Jupiter-like phenomenon of emission, but they also seem to have very small surface level magnetic structures like you see in the Sun around active regions, which also accelerate electrons. So it might be two different types of accelerations happening on M dwarfs. Yeah.
Sorry, I think I'm not following really. So when you say it's Jupiter-like, you mean they have something like Io providing some?
Yeah, it's either acceleration because of the spin and non-co-rotation of the plasma with the magnetic field, which creates this electromotive force. So the acceleration then is happening away from the surface of the star. It's happening far away where the plasma is, because of its inertia, doesn't co-rotate with the magnetic field of the star.
So there's something other than just the intrinsic?
Yes, something other than the chromospheric activity which is causing, yeah. And this is important because understanding what creates the high energy particles in these systems is important to figure out what eventual effect they will have on exoplanets, right? And so and understanding the coronal structure is important to figure out what kind of wind the star has, because the base of the corona is the boundary condition for the MHD simulations of the wind. We cannot directly observe the wind of these stars, but if we have the boundary conditions, we can figure out what the wind looks like. So all of this feeds into our ideas of what exoplanets should be subjected to. And I'll give you I hope to have a slide on a concrete example of that, how we can relate this to the exoplanets eventually. Yeah. So Sana again, so once we kind of understand what the emission mechanism is, we can actually locate where the emitter is in the corona or magnetosphere of these stars, because we know where the cyclotron frequency will be equal to our frequency, and that allows us to do a lot of different things. So the simplest thing you could do, which I'll give you an example of, is to say that if you saw the emission, it means it was not free absorbed, right? And so from the point of the emitter to you, the source has to be optically thin for you to see the emission. It should be optically thin to free absorption, and just that simple requirement actually allows you to say some interesting things. So this is the upper limit on the mass loss rate of the star, which is obtained as a function of, so the blue points here are different stars which we detect with LOFAR, and as a function of X-ray luminosity of the star, and the black points here are previous measurements of mass loss rates. And so we have an upper limit here, because if the mass loss rate was more than this, the wind would become free thick to the radiation, we would not have seen the star. Just the requirement of free optically thin puts an upper limit on the mass loss rate, right? And so this is a much more direct way to not measure, but to put an upper limit on the mass loss rate, whereas many of the other methods which have been used before require more complicated modeling, where you have to model the astrospheric Lyman alpha signature. When the wind hits the interstellar medium, you need to measure the excess Lyman alpha signature from that interface region, which is a more complicated way to do it. And many of the previous measurements on the same stars can vary by more than an order of magnitude. So yeah, so that's something we're doing. So you can, and then you can, I mean, we are not experts in MHD simulations, So we can do some extremely simple things. So we can pick a star which has a known planet and then try to make some very simple model, like 0th order model of what is the dynamic pressure, upper limit on the dynamic pressure of the atmosphere of the planet, and then use a very simple prescription to say, okay, with this dynamic pressure, can the planet retain its atmosphere, right? And of course, by no means this is a physically motivated model. It's a very rough 0th order kind of model, but gives you an example of what we could do once we know what the wind of a star looks like. Sure.
And how far is that planet from the star?
This one is, I will have to look it up. It's 625b, so it's a very well-known one. My guess is it will be I think it's close to the habitable zone of the star.
I'm just wondering if like, this is an effect, like, if it's only for very, very close in planets where you can deflect the atmosphere, or it's for just trying to gauge the distance.
Yeah, I'll have to look it up. I've forgotten. Yeah. Okay, so another example which Mayank also worked on, so I thought I'll show it briefly before we move to brown dwarfs. Actually, how much time do I have? About 20 minutes, 15, 20 minutes. Okay. Is this star which we found again is one of the stars we detect, and what was surprising about this star was that this star was extremely quiescent. It had almost no measurable activity, and so we kind of started speculating of what is creating the radio emission, what is accelerating charges in this star. And so we kind of were predisposed to say that, okay, let's look for these magnetospheric acceleration mechanisms, because there's no chromospheric activity we can see or detect on the star in other wavelengths. And that's what is summarized here. So if you compare it with an active star like AD Leo, any activity indicator you take, I mean, the star is barely shows any activity. And so we were like, why are we detecting stars with like no activity levels? Because radio requires accelerated population, something above the thermal population in the corona. And so we thought that, okay, it could be like Jupiter, but it's also an extremely slow rotator. So the spin is not fast enough to accelerate charges. And so we thought that, we speculated at that time, maybe there's an exoplanet there, which is inducing emission on the star, just like Io induces emission on Jupiter. So we got very excited. We got so excited that we made an artist impression. And the energetics work out, a lot of things work out. Only problem is we have to postulate the planet. We need an independent confirmation that there is a planet with those properties. And the other problem is, if it is induced by the planet, we should see the modulation at the rotation period of the orbital period of the planet. And then we never saw the radio signal again. We've observed for almost 100 hours with it, with LOFAR. And so we're kind of puzzled. And some of that puzzle was kind of dispelled because our colleagues got Zeeman Doppler images of the star, and then they figured out that the field of the star is flipping, just like the sun flips in field every 11 years. And so for us, the beaming geometry is important for us to see the emission. So if you flip the field, you'll not see the emission. And so that remains inconclusive because the field is flipping in the star. The North Pole and South Pole are flipping. Yeah. And so the beam might be outside the sight line of the Earth. That's one problem. And of course, radial velocities could not find a planet which was more massive than the Earth at short periods, which we need for this kind of interaction. But there was a Neptune found, but 400 days is too far to have this kind of interaction like Jupiter and Io. But what's very interesting, which has made this source really intriguing, is there's a huge curvature. And so we now think that there is a massive planet or maybe a brown dwarf in the system. And so that could also be implicated in the radio emission. So we have some JWST time in the coming semester to make a direct image of this object. And then we'll know if there is a gas giant or a brown dwarf in this system. Okay, switching gears, I just want to flash this result because we are very interested, and then we'll go to brown dwarfs and exoplanets. So remember I told you that we don't just look for Stokes V sources, we also look for these bursts because we want to find coronal mass ejections. And so we think that we have the first detection of an extrasolar coronal mass ejection. So this is a dynamic spectrum, so frequency and time, and this is LOFAR data on a star. And like I said, we don't point at stars specifically, we just take any LOFAR data taken in the survey. There are always some interesting stars in 16 square degrees. And this just happens to be an unknown K dwarf at 40 parsec. And then you get this beautiful frequency sweep at the time scale of that 1 minute time scale, which you kind of expect a type 2 burst to be. for typical CME speeds of order like 1000 kilometers per second. And so we are pretty excited about this. So we are now going back to the raw data, which is saved at a much higher resolution, to see if we can find any microstructure in the type 2 burst, because that tells you a little more information about the physics of the superalphanic shock. And so, but the frequency sweep is pretty clear, and so we are quite excited about it and writing this up right now.
Stokes V?
This is actually Stokes V.
V.
Yeah, but the burst you can also see very clearly in I.
So is this of order 100%?
No, actually no, this might be Stokes I. This is Stokes I, sorry. This is Stokes I, yeah. But we see it in Stokes V as well.
And
Yeah.
it's highly polarized.
It-
highly circularly polarized.
It is, sir, we also see linear polarization. It's elliptically polarized. Yeah. So solar type 2 bursts are actually, they can be circularly polarized, but it's rare, and it's known, the emission, at the point of emission you only emit in one magnetoionic mode, it's O mode emission. So it is elliptically polarized, but solar bursts don't appear highly circularly polarized often. Sometimes they do, very rarely. Often they don't, and it is because they are happening close to the plasma frequency. So the propagation is not straightforward. It's not just because the refractive index gradient with frequency is almost infinite at the plasma frequency. They follow a complicated path, and that depolarizes them. Yeah. But in principle, at the point of emission, it's 100% in one mode. It's O mode emission. Yeah. Okay, so let's go down the mass ladder. So we were in M dwarfs, a lot of exciting things which are happening there. So we are really excited about what comes next, especially with the type 2 burst and the coronal mass ejection. We want to find more of those. So there's a PhD student who started last fall and who's trying to find more of those type 2 bursts, because we don't want to just find one. Nature doesn't make one of something, right? So there must be more in the data. But of course it's slow going because the data volumes are too large. They're there in many petabytes. Okay, let's go down the mass ladder. Brown dwarfs, which I'm very excited about as well, and that's last part of the talk. And so here's an example of how we find brown dwarfs. So here's the Stokes I image, and so I want you to focus on the source there in the center. And there are many other sources, of course. These just 3 arc minutes, and that's a Stokes V image. Okay, and you can see that all the other sources, these are all extragalactic sources, so they are not circularly polarized. So only that appears in a Stokes V image, and like I said, at this point we think it's either a pulsar, a star, or a brown dwarf. These are the 3 known circularly polarized emitters, and you can pretty easily rule out pulsars because pulsars actually show pulsations, and so a short follow-up observation can be used to rule out pulsars. How do you rule out a star? Well, you just look at an optical image. Our distance horizon for this kind of emission is like 50 parsec or maybe 100 parsecs. And so you cannot hide a star in 100 parsecs, and because there's no molecular cloud which will obstruct hide the star in the optical. So if you don't see it in the optical, it has to be a brown dwarf. You know that already. You just don't know what mass it is because the emission is not thermal. It could be a free-floating exoplanet which would be a bright radio emitter. It's not thermal emission, it doesn't depend on the surface temperature. So every time we see something like this, we are excited because it could be a free floating exoplanet as well. Okay, so in this case, it turned out to be a very late, this is the spectrum at that pixel. You take a spectrum, infrared spectrum, and then you compare it with a known methane dwarf. So this is actually what is called a methane dwarf. And so for people who would be interested, the spectral type is T7. So this is the end of the methane dwarf sequence. So think of objects with surface temperatures of the order 500 Kelvin or something like that. So these are very low mass brown dwarfs. These are actually pushing towards the boundary between a brown dwarf and a free floating exoplanet. So these are maybe like 20 or 30 Jupiter mass objects. And then we find the cyclotron maser emission from them. So that's exciting. That tells you that just using radio emission, you can start finding these objects. And the radio is not thermal emission. So the object could be extremely cold and bright in the radio, unlike the infrared, where it's thermal emission, so the object has to be hot. So here's the second one we found, but the second one we found was a known brown dwarf, so we didn't discover a new brown dwarf. But it's the second one we found, and in this case we could actually make a light curve as a function of time, and then we could actually make a periodogram, and just like we did with Jupiter, we actually see that there is a peak, in the periodogram, and that peak is happening because again these are rotationally modulated emission, just like you see with Jupiter, and you can figure out the period of the brown dwarf. And so a lot of this has been done with brown dwarfs. What is new in what we are doing is we are doing it at very low frequencies. So we are going to find objects which have very weak magnetic field strengths compared to what we could do before. So the hope is that our survey will actually find objects which are closer to planetary mass than the previous surveys had. And so we can measure the rotation rate. In this case, it's about 3 hours is the spin period. And surely there must be more. And so Sana, my student, is now taking the entire survey data and now making Stokes V images at 4-minute resolutions and trying to look for these pulses and trying to make these Lomskargel periodograms on every pixel on the sky to try to find more. And so those are the only detections we have so far, but we just got started by searching for more, because we said again nature doesn't make 1 or 2 of something, there must be more. So she has found some candidates which show pulses like this, but it is work in progress. So our hope is we are going to find colder and colder objects with just like 50, 100 Gauss magnetic field strengths and get closer and closer to exoplanets in our ability to detect these things. Because we are at low frequencies, we'll find these objects. Okay, and again once we find the object, we want to make light curves. We want to see if it is one of the 2 mechanisms which I showed on Jupiter. And so for the second object we found where we could detect the light curve, we actually took 8 more epochs with LOFAR to see what is causing the emission. Is there like a planet around the brown dwarf? Is it like the spin of the brown dwarf? And so we took more data. The other reason we took data was because, remember I told you that with Jupiter's radio emission you can measure the field strength of Jupiter. And this is the only technique we have to measure field strengths of exoplanets and the coldest brown dwarfs. Only technique which is considered viable, let's say. And so here is basically a prediction from dynamo scaling laws of how strong the field strength should be. But I have expressed the field strength in cyclotron cutoff. So this is the frequency below which you should be observing to detect this object. And as a function of age, and the different lines are for different masses of objects. So a lot of the previous work done at higher frequencies would be sensitive to these kind of objects at like many tens of Jupiter masses. But now we are covering this parameter space at lower frequencies. So the hope is we are going to eventually reach a Jupiter mass, like detect objects and measure the magnetic fields of objects of a few Jupiter masses to a Jupiter mass. So that's the motivation to do some follow-up and try to figure out what is the mass of these objects, what is the field strength of these objects. So Timo, my student, did 8 epochs of LOFAR follow-up of that object. So that's the original epoch, and these are the 8 epochs. These are again light curve, flux density versus time. And so with some collaborators, we also got AO data, and it turns out that this object is a little complicated because it's a binary, and we do not know which component is emitting the radio, because the radio resolution doesn't tell us which component it is. But what is interesting is that because it is a binary, we'll be able to eventually measure the masses of these objects. And so that is important to test these scaling laws which I spoke about. To test the dynamo scaling laws, because you need to know the mass of the object to predict using this law what the field strength is. And brown dwarf masses are notoriously hard to measure, but not if they're in a binary. You can measure them dynamically. So it's good and bad news. So anyway, with 8 epochs of data, you again can take a Lomskargel periodogram. And so when he took the periodogram, we found the peak which we had found with just that one epoch. That peak is still there. So that's good news, roughly 3-hour rotation period. But there's also a second peak which is not there in the sampling function. And so we are right now speculating if both components are emitting, and you're just seeing the modulation because of the spin of both components. If that is true, then it's pretty interesting, because the second peak here is at about 0.8 hours, which is quite close to the rotational breakup limit of a brown dwarf. So here is the stacked image of all the 8 epochs. You clearly see the detection after proper motion correction, of course. So this is just to convince you that we are actually seeing the object in most of the 8 epochs. And so like I told you with Jupiter, here's Jupiter, let's say, here's the actual measured radio spectrum of Jupiter. It cuts off at a frequency which is equal to the cyclotron frequency at the surface, because you cannot get emission from below the surface. But you can get emission from far away from the surface at a lower cyclotron frequency. So to measure the magnetic field, you need to find the cutoff in the radio spectrum. A detection only gives you a lower limit on the magnetic field. So we tried to do that, and so far it is behaving the way you would expect Jupiter to behave. So here is just the scaled emission of Jupiter. I have just scaled it to different magnetic field strengths. And again, flux density versus frequency, that's the LOFAR detection. And we got additional data on GMRT and VLA, and they're all non-detections. And so for now, it is I mean, we need to get more epochs here to make this really solid, because like I told you, cyclotron emission is also time variable because it's a maser mechanism. It doesn't have a stable brightness. And of course, we actually had overlap between the observation epochs. And so that gives us confidence that this non-detection means something, because at the time of non-detections, we had detections with LOFAR. Yeah, so if you naively take this, so these different curves are for different scaling. So 10 times Jupiter's field strength, 15 times Jupiter's field strength, that would be the expectation for the cutoff of the emission. And so you get a very rough upper limit of 15 times Jupiter's field strength. So about 200 Gauss of field is what you would get to explain the cutoff which you see in this emission. So we're pretty excited about it. Timo is very excited after reducing all of that data. So you can put a line there. That's what you expect to be the surface magnetic field strength of this object. And like I told you, the one complication here is it turns out to be a binary. So those are the two masses of the object. And you can see that the mass errors are very large because we don't have a dynamical mass yet for this. But once we have a dynamical mass, then we'll know which one of these curves this object is supposed to be on. And then we'll be able to test whether this dynamo scaling law is correct or not. And this is the scaling law that's the best law we have to predict field strengths of even exoplanets now. So, okay, so that's about brown dwarfs. Let's go to extrasolar systems. You need to now go lower in frequency to actually go from brown dwarf to Jupiter. So remember, Jupiter's emission cuts off at 40 megahertz. So you need to make the same, we have to do all the things we did right now with brown dwarfs at even lower frequencies. And going to even lower frequencies is extremely challenging because of not just radio frequency interference at these frequencies, also because the ionosphere of the Earth creates a lot of corruptions on the wave front. And these ionospheric effects increase as square of the wavelength. And so that's why we have a lot of technical challenges to solve, and one of the students working on it, and we now have images made down to 15 megahertz. And so we are hoping that just like we found brown dwarfs, we'll find exoplanets in these images. So yeah, that's basically where we are, and I'm going to stop here. Those are my conclusions, and I'll take questions.
Questions, comments, anything? Yeah,
Very nice talk.
Thank you.
Learned a lot from your talk. Maybe just a very general question or comment. Observationally speaking, what are the challenges that you do face to observe those objects that are below the cyclotron cutoff frequency?
Yeah, so the thing is, if you want to observe objects whose magnetic field is very weak, you have to go to lower frequencies, like you mentioned. Observationally, the challenge, there are a few challenges, but the main challenge is the galactic synchrotron emission is too bright at the lowest frequencies. So the most of the noise contribution is not from the receiver, it is just from the sky. And so it's very hard to get high sensitivity at these low frequencies because this bright glow from the galactic cosmic rays, that's one. The other is you do not know a priori which object is going to be emitting towards you, or which object has bright enough emission for you to detect. And so if we already knew a priori that this is the best, we would just like integrate deep on that object till we find it, but we don't know that a priori. Like the best object in terms of all these properties the geometry could be such that the emission is beamed away from you. And no matter how much you integrate, you'll never see it. And so the problem is you have to try too many things, like you have to observe too many objects to get a detection. So telescope time is sometimes a problem. So we circumvent that by piggybacking on other observations. And the final problem, of course, is calibrating at these frequencies. So because of ionospheric phase fluctuations, you're trying to do adaptive optics basically. And sometimes there is not enough signal to noise ratio to solve on the time scale over which the ionospheric phase is changing. So your adaptive optics fails, and then the image is defocused, and those are the technical problems. Yeah.
Other questions? Yeah.
So in your low frequency search, you're also basically looking for circularly polarized low frequency point sources?
Yeah, point sources circularly polarized. We find pulsars also.
And time variable.
The time variable is not a filter, but they all end up being time variable.
Why is it not a filter?
We don't need to. I mean, AGN are not circularly polarized.
I see. The circular is the smoking gun.
Sir, yeah, exactly, yeah. AGN are known to be circularly polarized below 1%.
Yes, sir. But they also vary, so that doesn't.
They also vary. Well, at these frequencies, they vary very slowly, because the frequency is very low. They vary over months at these frequencies. Yeah.
Yeah, Christian.
Yeah, very, very nice talk. Very interesting.
Thanks.
So at the beginning, you mentioned that if we look at the quiet sun, then the emission is dominated by Jupiter, maybe because of the interaction with Io at very
Long wavelengths.
long wavelength, right?
Yes, yeah.
But then you also said that sometimes the active sun will actually be above this emission.
That's correct, yeah.
For a star like the sun, what fraction of the time in alien civilization we'll see a quiet sun, and what fraction will be like an active sun? Do you have any
Yeah, no, most of the time the sun is quiet. The majority of the time it would be the quiet sun with just the background gyrosynchrotron component. The sun being active, it's not really a Poisson process. It's not that random. There is always a period in which the sun is extremely active, and you kind of have an intuition for that based on not just the 11-year cycle of activity on the sun, but also you know that like even auroral activity on the Earth, which is related to sun's activity, has this good active periods where you get to see a lot of aurorae for over many days, and then there are long periods where you don't get many. So it's a little bit like that. Yeah, it's
last week the sun was 10 times.
Exactly, it was completely crazy. Right? There was people saw aurorae from Amsterdam despite all the city lights. Yeah.
So just want to follow up very quickly that question. So then when we move to lower mass stars, right, they become more active as long as they're young, like M dwarfs, right?
Yes.
Does it mean that it will be somehow easier to detect a Jupiter-like planet around a early type star like G or that's not so active?
Yeah.
We go to M dwarf to
Yes. Yeah. Yeah.
I don't know. I suspect.
No. It's a very good point.
That
And
it will always be shadow this Jupiter-like emission by the star itself. Is that?
I think it's a very good point. And my current thinking is that yes, but for a slightly different reason, which is that we now know that M dwarfs will produce cyclotron maser emission. On the sun, it's quite rare to find cyclotron. Most of it is plasma emission related to these flares, which I spoke about. Now, if you know there is a gas giant exoplanet and you detect cyclotron maser emission, you don't know if it came from the star or the planet. But if you see it on a G dwarf, then you're more confident it comes from the planet. But of course, there is a way to figure out if it comes from the star or the planet. It is to see the rotational modulation. And by looking at spot modulation on the star, you know its rotation rate. And if you find radio emission which is modulated at a different rate, you know that you cannot produce it just from the star. There must be either a star-planet interaction which produces the emission at the synodic period of the planet or directly from the exoplanet itself. Yeah.
Other questions? Yeah, no.
Hey, you mentioned this detection of radio emission from the cold low mass.
Yeah.
particle, right?
Yeah.
So that means you really need the electrons. So
Yes.
source of the electrons
Yes. Yeah.
for this low.
Yes.
energy.
Yeah.
I don't know if it's L or T dwarf or even. or
This was late T dwarf. Yeah.
late or very,
Yeah.
very late. So
Yeah,
it's
yeah.
not source. Because for the Jupiter you have these solar winds, right? You have
Yes.
these solar winds and they bring the electrons.
Yeah.
And what's
So that's a very, very nice point. It is a debated question. So no one knows the unique answer, but I'll just make a few comments. One is, most people will be surprised to know that the primary source of plasma in Jupiter is not the solar wind. It is Io is the primary source of plasma.
So you are saying all gassy.
Yes, yeah, because of tidal forces. Io is the most volcanic object in the solar system because of tidal forces. Yeah, so these could have moons, and that could be the source of plasma. So there's a
Yeah, you want to slight sensitivity to
Good.
yeah.
You know, the tidal heating produces all gases.
Exactly. So yeah.
Perturbation, right? From another planet. From another moon. This is like a Galilean moons, right?
No. Io has tidal heating.
Tidal heating is driven by eccentricity.
Yeah, but very small. It's mostly a circular orbit in Io. It's enough to make it volcanic.
But the stem peels, nominal work on this.
In brown dwarfs.
He predicts that the volcanic eruption is due to the eccentric orbit.
That's the thinking. That's currently the thinking that's what causes Io to be so volcanic. Yeah, and so the expectation is that these objects will also have volcanic moons around, exoplanets or moons, whatever you want to call it, around them. But there's no confirmation of one. So that's why I said it's still debated. The other thing is, once you start this process, it is self-fulfilling in the following sense, that the electrons which are accelerated precipitate in the atmosphere. It is the reflected emissions which create the radio emission. But some of the electrons precipitate in the atmosphere and they create the aurorae. That's why it's called auroral radio emission. I'm sorry, I didn't use the terminology, but it is used because it's the same electrons which create the aurorae on the planet, on Jupiter. And so once you get this process going, the aurora will ionize the atmosphere and you will create plasma in the magnetosphere. But that is a chicken and egg problem. That is harder to solve from first principles. My personal feeling is that many of these probably have moons or exomoons, exoplanets, which are outgassing, creating the plasma in the magnetospheres. Yeah.
Just curious, in the HR diagram you show there is one Y dwarf with the circular polarization detection.
Yeah, the MSP.
The pulsar.
Which one? I think.
In the HR diagram.
In the HR diagram. Let's go. This I think this is it is a millisecond pulsar. I don't know if it's millisecond, but it is not the white dwarf that is emitting, or at least that's what we think. I think there's a pulsar in that system. Yeah.
Okay.
Yeah. That's fun. I could actually mention there's another star where it's a K dwarf. That's not seen in LOFAR. It's actually seen in the VLS sky survey. But we know that there is a white dwarf in that system as well. So in that case, we are actually speculating maybe the white dwarf has something to do with the radio emission. But in this case, I think there's a pulsar. I'll confirm, but I think this is the one with the pulsar. And so yeah, once there's a pulsar, there you know what produced the circular pole. It's probably the pulsar. Yeah.
Any other questions? Comments, suggestions? If not, then let's thank the speaker once more.
Thank you.